detailed results of our FPVN project. Let's start. The agenda, the task of the FPVN project, work package 3, and then the life cycle story, the pump life cycle story as an example, a very small recap of the life cycle approaches. We had a session about that, and today we should have a deeper look at the further FPVN work package 3 results, and I will end with a conclusion. The task is of our work package 3 to explore major industrial data models and to set up a semantic interface between STEP, two application protocols. Torbjørn will explain that, C-Force DEXPI, and of course using in the middle IDO. And we use the pump life cycle story as example. And in the beginning, we have a process defined with the pumping and storing material and chemical reacting as a unit operation between some streams and for the connection, the inlet and outlet port into different diagrams as a block flow diagram or a process flow diagram, same content. And then with DEXPI, with a process plant, we have a pump system, we have two piping network systems, we have two vessels, one for storing, the other for reacting. And for the pump system, we have the pump itself, a motor, and a measurement function to control the health of the pump. That is a little part of the pump life cycle story. And of course, we need the relations between the process part and the process plant part. And that will be perhaps between the unit operation and the specified equipment from the pumping unit operation to the pump system, or from the storing unit operation to a vessel, and from the reacting chemical unit operation to a vessel as well. And we see here a motor, and we see the measuring function. From the process streams, we have to set up the connection to the piping network systems, and from the ports to the nozzles. That is a task we have to model with IDO. And beyond DEXPI, there is a world of the equipment, of the physical assets, and that one is not part of the DEXPI's process specification, neither than from the DEXPI plant specification, but in our use case, it's also a part of the use case. And we have to model the assets itself and the relations between the asset and the plant object. That is part of our whole pump life cycle story. And this one, we have this input modeled as an XML file, and this XML file, I will show a little bit about that. Yes, we see all the things I mentioned. We have the parts for the part for the process. We have the part for the specified process plant. We have the part for the actual assets. And we have the bridges between the process and the specified process plant, and from the specified process plant to the assets. And here we see, okay, we have the process itself, then the process step, then the unit operations, the different one with its ports, the first one, the second one is the pumping, and here we have a property as well, and the ports from the pumping unit operation, and the third unit operation, the the reacting unit operations. Then we have for the process connections, the two streams which we had in our model, and we need that one. That is our part which we will model with IDO, and I will show some results for that modeling part. And the next part is the specified process plant. There we have the whole process plant, the plant section, and the pump system. And for this pump system, we have the specified pump. And then we will see the specified pump has a property differential pressure. And we will see more that there are the centrifugal pump as specialization of the pump here in the middle. This one has properties upper limit and lower limit design as well. And here we see more the nozzles and the motor, and the motor will be specialized as alternating concurrent motor, and we see the measurement function in it, in that file. And if we go to the next part, the specified, we had it, and then we go to the actual one, and the actual plant, there we see, of course, we have the whole plant, we have the plant section as actual, and we see the different assets or equipments, physical equipments, the actual centrifugal pump with some properties, and the measurement system, and the alternating current motor. And then the last part, that were the relations between the different objects. And there we see, okay, from the unit operations, we have some bridges to the specified plant items, and from the specified plant items, we have some bridges to the actual one. That is the input we modeled from the picture, and let us have a look how it is modeled. A little recap from the whole life cycle. That was a picture from the BIM community, and here we have the process in the left upper quadrant, and in the left lower quadrant we have the processed plant with the blue part, the functional part, let's say the pump, and the physical objects, let's say the specified centrifugal pump. To the right we have then the assets and the producing plant. And the left two ones are specified, and the right two ones are the actual objects. That is then the combination of the BIM picture with the process industry life cycle picture. And the relations between, we had it some weeks ago. There we could model the relations, the first big bridge from the process to the plant, with LIS has participants, vice versa, LIS participates in, and to the right, the direction between the plant and the asset, LIS implemented by and LIS implements. And we had some, on instance level, we use this one with object properties as described, and the object properties LIS implemented by, and the inverse, these two ones here, they inferred that will be the LIS classification, LIS specified and LIS actual. That is done with this on instance level. And now let's go to the modeling results more, a little bit deeper. We start with the upper ontology LIS, and on the bottom, let's say a DEXPI file. And here we see in the middle, we need some more reference ontologies to, let's say, that we are able to model the pump life cycle story with the upper ontology LIS. We have here first we use for the unit of measurement system QDT, and we have to add some QDT specifications, and we have, let's say, the domain-specific things where we have to model all the properties we need, all the classes for the process, for the specified plant, and for the physical equipment, and we have to model some assignments. And in the top of the reference ontologies, we need additional object properties. The first one. Then we need additional property aspect definitions, value aspect definitions, and data type extensions. Here we have them, and that is a huge work which we have done, most of that done by Andreas Neumann. And we can show them perhaps in that way if we have the whole atmosphere and the height from 0 to 500. The upper ontology is perhaps from 10 kilometers to the space, and we need reference ontologies to bridge from 1 kilometer to 10 kilometers. And let's say that is a picture that we can bridge from DEXPI to LIS with some additional definitions, and we use them. And I will show now some details. First, detailing more the process part in the beginning, where we had the unit operations, the different 3 ones for pumping, chemical reacting, and storing, and we have the ports, and we have the streams, and we have the upper, the whole process, the process steps, and we completely modeled this as LIS with LIS activity, and it's the process modeled is a complete activity network. And we had some additional object properties to support the connectivity between the unit operations streams. Oh, sorry. Kann ich später zurückrufen? Okay, sorry for that interruption. And now we have this completely modeled. And this looks like that we have at the top the classes from IDO. Then we need additional classes, the processing activity and support activity, done in the additional ontologies for object properties. Then the relations always to part 4. Then the class definitions in the proc ontology, and below the DEXPI instances. A modeling pattern for that could look like that. We start with the process and have an exact match to part 4. The same with the process step. And then we have the pumping as unit operation, and the pumping itself has an exact match to part 4 and the unit operation as well. And we relate them to the LIS classification. LIS, as I said, everything LIS activity classified, and for the additional to have domain and range restrictions for the object property, there is an additional processing activity defined. Now we have the different instances in yellow. We have one specific process. We have one specific process step, which is part of the whole process. We have one specific, the pumping unit operation is part of the process step, and this one is modeled in that way, the special pumping unit operation. Again, we start with pumping, then we say, okay, we have the material port and the streams, we need them, and we have classified them all as LIS activities. And as I said, we need additional object properties, classifications for processing activity and port activity. And now to the instances, we have the pumping instances is of type pumping. Then it is part of the whole process step, and the pumping has a material port as part, and this one, here we see the object property feeds, and the material port feeds the pumping. And then we have an additional material port, and this additional material port, that is, here we see the other object property delivers to. From this pumping to the next material port, we have delivers to. And now we have the streams, and the stream delivers to the material port, and the stream itself is part of the process step, and the other stream as well. And now we have nearly a complete picture how the pumping instance as a unit operation 002 is modeled with LIS and with additional ontology definitions. And this one we could have a look how it did look in Protégé. I try to open the prepared file for that. It should be this one. And now we see, okay, the different, we are in the past temporal, and now we see the different activities we had, beginning with process steps, the unit operations, pumping, reacting chemicals, storing materials, the streams, and so on. We see the used individuals, and I hope I try to start Hermit, and Hermit is happy with this kind of specifications, and we should have a little look to the inferred one and to the individuals, and we see they are there. It works, and the reasoner is happy with this kind of definitions. Let's go back to the specifications, and let's go to the next big part of information structure, that is a specified plant. And here we see we have the different classes we need, all have a prefix specified, and we have the relations to part 4. And what we see here, we have the specified pump, and here we have a pump. That means part 4 has a broader definition. The pump definition in part 4 covers specified, and later we will see actual pump as well. Therefore, the specified pump is only a subclass of the part 4 pump, and all in the color blue functional objects of the specified plant were modeled in IDO as LIS systems. All the green ones are modeled as inanimated physical objects. And what we should cover more is that the specified centrifugal pump is subclassified to the specified pump. That is the internal bridge between blue and green here from the system to the inanimated physical object. Let's say from pump to centrifugal pump. The same is used from the motor to the alternating current motor. Internal bridge between blue and green, between the functional and physical objects modeled in LIS, blue ones as system and green ones as inanimated physical objects. And for the specified pump, I will show some modeling pattern, and the modeling pattern, they are based on the required properties for the specified plant, and we will have a look how they are modeled. First of all, we will have a look at an identifier, and the other thing we have in more detail look how the differential pressure is modeled as a property from a specified pump. And what we see more in on this slide is we have two types of properties. And there was a long discussion how to model properties. And we have the two groups, the assigned properties and the dependent properties. And for this, we have to use different branches. 2 weeks ago, Dirk has a good presentation about the concepts from IDO with the three main branches from dependent, from object, and from temporal. And in this one, the assigned are modeled in the object branch, and the dependent are, as the word says, in the dependent branch. And here we tried to model once the identifier and one time the differential pressure. One assigned and one dependent. And what we see more is a cardinality. And the cardinality says, okay, this property can be assigned to a specified centrifugal pump. It can be assigned, and maximum assignment is one time this property. But we always say only the identifier, they are necessary. They get the cardinality 1, and all other, it is possible that in the view of DEXPI, the specification should be transferred to the next one, and this specification can be incomplete, and therefore for incomplete, okay, perhaps this specification there is no value in the moment for lower or for upper limit design. And now let's have a look at the modeling pattern from an identifier. Here we have in our example a specified plant section as class definition, and then we have a property defined, the identifier, and it is in the branch of object, sub-branch information object, classified that, and a relation to part 4 for the identifier. And then we need an additional definition, an additional class definition, identifier assignment activity, and this one is modeled as activity. And then we have an hour restriction defined that this activity could be used and should be used one time to relate this activity to this plant section. In this picture we have no direct modeling relation from the identifier to the plant section, only we have an additional assignment activity, and this assignment activity is related exact one time to the plant section. And on instance level, this one, the special one, we have the special plant section that needs an identifier, and here we have the information object as shown, and this information object has an instance, the identifier, and then we use the assignment concept. We have an instance from the assignment, and this one is now with the list object property has passive participant related to each other. And what's missing in this picture or not considered in this picture, we could use list has active participants if we would say, okay, this organization has done this kind of assignment. And here we need an additional object property to relate the value to this instance, the identifier. That is now a picture how it could look to use assigned properties. In that case, we have the property identifier with its value assigned to this specific plant section SE001. Okay, let's go to the next kind. That was the differential pressure. Now we are in the dependent path of LIS, and we have a specified pump, and we have a differential pressure. A differential pressure modeled as property. Of course, this property could be used for different classes. In that case, it will be used for the specified plant. And we see now we have a restriction definition. And this definition relates this property with max qualified cardinality 1 to the specified pump. Now we have on the property or on the class level definition, we have a relation from the class to its property differential pressure. And we have some additional restrictions to say, okay, as I said, we need an ontology for data types. We have related it to double measurement type datum, and we have object properties aspect. It is a differential datum, and it's a calculated datum, and the relation on this level that it is every time, for every instance of the class, we use the relation to QDT. It is pressure and it is absolute pressure. And on instance level, we see here the instance, we have a special pump, P001, and this one with LIS has quality. There is an instance for the property, and the property, there is an additional instance for the value of the property, and they are related to LIS quality quantified as. And the last instance, there are always the 3 instances, and the last one has the real value with LIS datum value and has the real unit of measurement bar. And this one, the bar, there is an additional restriction which checks that it is a unit of measurement which is related to absolute pressure and also part of the DEXPI specification. This is now an example, the slide before on class level, and on this level, on instance level of dependent property. Looking on the watch, I say, okay, we could go to very quick to Protégé, and I load that one before updated, and here we see all the instances I had a look on. Here is the pump, here's the nozzle of the pump, here's the differential pressure with its value, and the same not right with upper limit design pressure and upper limit design pressure, the value for that. All loaded into Protégé. And for the actual pump, we have additional classes. Here we see that we need the actual one, and these are all modeled as inanimated physical objects. And let's come to a conclusion. What I have shown was modeling pattern for the process, for the classes, breakdown structure, unit operating, pumping, and the internal topology. For the specified process plant classes, one example, dependent property, another example, assigned property. For the actual process plant, the classes, and as recap of the life cycle story, the bridges between process and specified process plant and between process plant and actual process plant. And the pump life cycle story was modeled successfully. the project identified the need of several additional ontologies between DEXPI and IDO from 1 kilometer to 10 kilometer, let's say. The results need still to be verified by the IDO team. The proposed additional ontologies must be further extended for industrial application, and all the documentation, all the files I have shown is available or will be available on the PCA web platform. And now I hand over to Torbjørn.
Yes. Can you hear me? Can you see me?
Yes.
We can, yes.
Great. I will talk about a little bit more about how we have used DEXPI, some other standards, and transform them to our 2D and work with them under the umbrella of IDO in the use case 2.9 of Arrowhead. It's about a knowledge graph-based digital twin, and I will explain how that's done. Why DEXPI in use case 2.9? And the use case is about the process graph. And to be able to do what we was planning to do, we needed to know how things were defined from a functional point of view, but also how things were combined and connected to resolve these functions. We wanted to be able to do this so we could do connectivity traces, we could do life cycle checks. How has this function location, how has this tag been realized over time? How many times has it been replaced? How many times has it been repaired and so on? And we did this through combining DEXPI with STEP mainly, the ISO 10303 standard, to be able to cover the rest of the life cycle with the realization, keeping track of possible realizing equipment types and so on. And if you look at this, we have the engineering domain. In this area, engineering is very much done by process diagram and PIDs. And we got this, and it worked very well. We used DEXPI output, and we generated OWL representation, triple store or triples for the data on PID. So we have a DEXPI ontology, we have equipment, instrumentation, process topology, connectivity or system topology, and engineering properties in one ontology. We have used V3C technology and IDO as an upper ontology to align this DEXPI graph and using different ways to align it, different ways to step and We have also used it to Arrowhead, which is Arrowhead framework, which is the how a system behave in real life. So that's about sensors, real pumps, real fluid medias, and so on. We use CFOs to do classification and allowable properties. And CFOs is based on 5926-4. We also use things like Cadmatic, which is a system for 3D visualization for sensor data. You don't like to have all sensor data in the ontology, so we store them in time series database. InfluxDB we use, it's an open source database, and we use this ontology to do IT and OT harmonization. That means that we use Knowledge Graph Foundation for this in 2.9, RDF OWL, Sparkle, Shackle, Rules and Reasoning, other semantic APIs, secured and governed access, and all stored in graph databases. And we've been using a tool from GraphWise called GraphDB. So this is the reason why we have used the engineering domain, the PIN ID and DEXPI is of course that's what's used in this industry, but also that it fulfills the needs for simulation, for analysis and connectivity. And we added the things with 3D visualization for 3D context evaluation. We did add things for life cycle evaluation, and we used connectivity to do connectivity evaluation. We used Boulder Brooker from Semantum. They are a partner in the 2.9 use case, and they have the capability to go from PDF file format, DEXPI or PIN IDs, and translate that to RDF. From the beginning, they translated everything to Proteus files, XML files, but now they have also a way to get RDF out, and that really helps. That means that the big hurdle to go from PIN IDs to semantic web is more or less gone. They deal with software features like symbol recognition, text recognition, and connectivity recognition. Next slide is about their support for RDF. And in our case, it was really, really good. We did it first once by hand, and it took a lot of time. But now we get it just by as an output from Model Broker. Is that we add also the life cycle data or the life cycle graph to the engineering and DEXPI graph, because then we cover it from engineering to maintenance and rebuild and so on. And we do the alignment using IDO. We have DEXPI concepts and we have step concepts, and we align them, and very successfully. We had like in step there are like 1024, I think. It is very detailed classes. Out of these, we have aligned about 20 of them, but still we can traverse this and use this as one one knowledge graph, even though there are like 3 or 4 of them. And we can go back and forth using this alignments and so on, and do very interesting analysis. So we are not translating anything. We are making explicit and autonomous ontologies play with each other using IDO and alignment technology. And that's a large and very good benefit. And we can do things much faster, much easier. We can add new aspects of a plant, adding a new standard to it and align it with the things that we already have. So we align, the overlaps are good, and we can align these concepts, and then we have an interoperable set of knowledge graphs. This is the main architecture of the digital twin architecture. We have here, up here, we have, we saw this 4 quadrants of the BIM world in Heiner's picture, but this is the requirement, function requirement, and other requirements, and down here is the specification of solutions. But some specification of solution is dependent on services or functions on the next level. So there's an iteration between and building this structure with this kind of structure, so we know exactly what kind of components we need to have lowest level of components, and how to build this up to a function that supports theoretically this. But this is not enough that we should be able to do it theoretically. We need to realize all the components needed, and that's either you specify something to build, or you design a component yourself. But that's a realization activity, and that moves you over to the realized component part of this. And these are then components that are built together in a configuration, and they are realizing the real system. So this is the plant, real plant, the real persons, real kickable pumps and so on, while this is the functional requirement, the need that one should resolve. And this is help us very much to get to know where we are in the life cycle and so on, because not everything is at the same life cycle at the same time, life cycle state. And of course, a large plant there is always rebuild and maintenance going on, so we need to have it this way. We are right now working with 3 different levels. We have the upper ontology, we have domain ontology, the DEXPI ontology, the step core ontology, and arrowhead ontology. This is about specification of functionality. This is the realization of functionality, and this is the behavior of the real system that will. And there's an arrowhead ontology built on the microservice-based architecture that's in use. We are using classification schemes from CFOS. CFOS is based on ISO 15926-4, and that is tag classification, equipment classification. So tag is classifying things here. Equipment classification is classifying things there and there. And but it also specifies allowed properties for this and for this, and they are different because these are the physical things, and these are the requirements and the specifications, identifiers, and so on. You have a semantic knowledge graph and services, RDF, OWL, Sparkle, Shackle, and other APIs here. We are not supporting GraphQL. I don't know this old slide. We digital twin capabilities. We keep track of function locations, tags. We have part and part individual traceability, activity and nomination of new parts, maintenance activities, RFID of physical identification, IT, OT interoperability, and analysis and visualization. And we are demonstrating this in the demo that we are doing right now. We are using the technology stack standard from V3C. We also deal with support maintenance activities. We have DEXPI engineering, which is aligned with the step life cycle, and the step life cycle deals with part types and individual part types. And these things are used to do the maintenance activity. We create work orders. We create work requests from the Arrowhead system with the sensors and the OPC UA signals, and then we check the signals coming, the sensor readings, and we look for if they are inside or outside threshold, or if they are loud, or if the trend is going in the wrong way or so. And we can create issues, and the issues are evaluated to be able to create work requests in SAP. SAP is then adding them to the knowledge graph, the step part of the knowledge graph, and the step and these work requests are then investigated by engineers to finding out the constraints coming from geometry, from the 3D world, from history, life cycle history, and also about connectivity, and decide what to do. And it could be that they should repair a pump, or they should replace a pump, or what they should do. And that's created in a description of the maintenance activity that's fed back to the SAP mockup. We have an SAP mockup since we couldn't use the SAP that was running. So we have a mock-up for that, and that generates a work order. The work order is executed, planned by SAP, and then we get a technically complete work order from SAP, and that's integrated into our triple store, into the knowledge graph. So that's enabled by using all the foundational information from DEXPI. We emphasize that we are not doing translation. Translation is the red part on the left. Instead, we are doing interoperability, and we are alignment based. We align things with each other, and that way we combine different knowledge graphs, even if not everything, all semantics in the knowledge graph is aligned. So that's a little bit different to what the goal of what Heiner was talking about. We are aligning very small parts of the knowledge graph to enable fast development and fast return on investment. We don't say that it's not good to do very rigorous alignments, but we can get value out of such a project just after a few months instead of several years. And I think that's needed. And we can also add new knowledge graph, or we can replace old knowledge graphs easily and still have the same system running. So that's one of the things that we have been very successful with in use case 2.9. We are not going for translations, we are going for interoperability, and we align on a few things. This is what we also do. We can walk from the knowledge graph side to the right, and we could click on something there, and we could see where it is in the 3D world, and we can click on something in the 3D world and get to the correct class in the knowledge graph. This is used to understand, to add 3D in the understanding of all the symbols. It could be very close on the 2D PNID drawing, but very far away from each other in reality. So, conclusion.
We have
Traditional
only,
engineering exchange.
we have only a
Yeah,
couple of minutes.
that's last slide. Last slide. We can do this. It works nicely. We do it by having RDF, our knowledge graphs. We deal with semantic digital twin ecosystem, and we are also using a combination between SysML v2 and the PNID, because they are supporting different industry. That was all. Thank you.
Thank you, Torbjørn, and thank you, Heiner. We have a few minutes for questions. I cannot see anything in the chat, and I don't have any hand raised, but are there any questions? Someone who wants to start?
Hello,
Yep.
this is Gregor from DEXPI as well. When I look back to another training session where Onno presented C4 semantics and another training session where we had IDO details, there was a recurring topic, the topic of properties. And in the example of Heiner, I saw something like Liz quality. Is it just one example or one idea of how to address this property issue? Or is it already aligned? What is the status of deciding if a certain pressure is, for example, a dependent or an assigned property? So could someone give me a hint? What is the status of what was shown regarding the quality and the pressure gauge property? Heiner?
In our modeling, Gregor, we try to use that in the dependent branch. If we know that there are discussions if it's the right one or if it should be possible in future to have such kind of property in two branches. But that is, as you asked, Gregor, an open question, and we have to bring answers as I had said in my conclusion.
Okay.
In the moment, it's only the presentation how two different properties could be modeled, one in the dependent branch and another in the